to explain this formula. On the left-hand side, V of R is potential at location at a certain position R due to a particle. In principle, actually, it is also valid for a spherical uniformly charged object outside of this object. K is Coulomb's constant, Q is the charge of the particle producing the field, and R is the distance from the point of interest to the particle. All right, now I started to talk about the effect of substances on electric field. If we have certain electric field in space and we put substance into that electric field, it is going to affect the value of the electric field. In general, substances affect the electric field. And how the substance changes electric field is characterized by the certain property of the material referred to as dielectric constant of that substance. Dielectric constant, we use Greek letter kappa to represent dielectric constants of various substances. In this expression here, E sub 0 is the electric field in vacuum, and E is electric field when the substance is inserted into that field. In dielectrics, kappa is greater than 0, so electric field is always weakened. So let's imagine this situation. So let's say that we have certain source of electric field, like for example, could you recognize what system could create electric field like this? So these are electric field lines. If these are electric field lines, what would produce such an electric field? Parallel plates, two oppositely charged parallel plates. From this drawing, we recognize that this is a uniform electric field. So vector E0 is the electric field vector describing this electric field. So at each location, you have now to imagine that there is an arrow E0. Now we are going to place a substance into that space. If we place the substance into that space, the charged particles within that substance are going to align themselves in a particular way. And for dielectrics, it is easy even to comprehend why does it happen. Because electric field now, that external electric field is upward, which means that it pushes positively charged particles upward and negatively charged particles downward. Even in an insulator, I mean, like water, for example, we cannot separate charges in the molecule. Hydrogen atoms are going to stick with oxygen. That external field will not tear apart molecules. However, because water molecules exhibit dipole moment, they will realign themselves in a particular way. They will turn themselves with the positive charge facing upward and negative charge facing downward. So if I take a look, for example, in vicinity of this, actually, how about if I think about this surface? I see that this surface actually is not charged because I have positive charge, negative charge, positive charge, negative charge, positive, negative, and so on. So inside, actually, the distribution is still pretty uniform. However, see what happens at the surface. Over here, when we have the last row of molecules, then on top, we are going to have positively charged atoms belonging to a molecule. And at the bottom, we are going to have negatively charged atoms also belonging to a molecule. Well, so now we can see that the top surface is charged positively, bottom surface is charged negatively. Now, uniform electric field produced by two parallel conductive plates is produced not because they are conductive, but because it is easy to distribute charged particles along them. So over here we have the same situation. Now, this surface is charged positively, this surface is charged negatively. These two surfaces also will produce electric field. Now try to figure out what kind of electric field the two surfaces produce inside of that substance. What is the direction of electric field? Well, and how about if I say that this is upward, downward, or sideways? So who votes that it is upward, that the electric field produced by the reorientation of molecules in the substance is directed upward? Who believes that that field is directed downward? Actually, more people believe that it is directed downward than upward. Who believes that it is sideways? That's good. And who has no opinion? Still too many. The correct answer is downward. In order to produce this external field, to produce a line like that, well, this corresponds to an upward electric field. The bottom plate has to be positively charged. The top plate has to be negatively charged. Now, in this dielectric, it's the other way around. The top is positively charged, bottom is negatively charged. You should also recall that when we draw lines away from the positively charged objects and toward negatively charged objects. All right, so here we see the reason, because now this electric field, the electric field which exists in the substance results from both fields together. The electric field produced by those plates of two parallel plates and the substance. So the resultant field here is smaller than the initial field. And all substances for which dielectric constant is more than 1 are called dielectrics. And dielectrics are actually quite important in making certain type of devices, electronic devices called capacitors. We will talk about them pretty soon, because right now we discuss more generally what happens in nature, but later on we are going to think how to build electronic systems. Oops. Well, now how about if we put conductors in the field? Because even let's think about that previous drawing. If instead of having a dielectric, we had a conductor. Now remember that in a conductor, charged particles can travel. I mean, if it is a metal, for example, electrons can travel. So what would happen? What would happen if this were not a dielectric, but it was a metal in which electrons are not bound to atoms which cannot move, but they are free to move? What electrons would do? What did you say? They would just go through. Well, if there is a conductor feather, but if, let's say that if I just put a conductor in the field, the electrons, and which way the electrons would go? Up, down, or sideways? Why up? Because think about the electrostatic force exerted on the electrons. And so if this were metal, if you put this in the external electric field, let's say that initially we have a uniform distribution of electrons. Now, electric field here is upward, which means that electrostatic force exerted on the electrons will be there, because now let's recall the definition of electric field vector. The electrostatic force is equal to the charge of the particle multiplied by electric field vector. Electric field vector is up. We multiply by the negative charge of the electron. So we will get a vector in the same direction as the electric field vector, which means up, right? Is this the justification which you suggest? It's wrong. If I multiply a vector by a negative number, I'm going to get a vector oriented in the opposite direction. So electrostatic force is on electrons is exerted downward. Electrons will travel to that surface. And this site is going to be, therefore, depleted of electrons. So it is going to become positively charged. This site is going to be negatively charged. Electrons will travel over there, depleting this site. So the internal electric field produced by that metal will be which way? Up, down, or sideways? Who votes for up? Who votes for down? Down is correct. Now you see that. Yes, the electric field is going to be down. So we see that, that the external field of the metal is also going to reduce the electric field. Now think how far it is going to reduce. When the electrons from that volume are going to stop flowing toward the surface, because notice that when more and more electrons approaches this surface, that surface begins to repel small electrons. The surface becomes too crowded. So there is a point that the repelling of the electrons at the surface will be, can exceed the electrostatic force exerted by the external field. In this situation, those excess electrons will go back to the volume of the metal. Now, what will happen in equilibrium? Yes, Owen? Something is going to be zero. What? It's correct. Actually, not few things are going to be zero. Yeah, in order for electron not to accelerate toward one surface or the other surface, the electrostatic force exerted on the electron has to be zero. Well, when we can get electrostatic force, what can we say about electric field if the electrostatic force on the electron is zero? Very good. Electric field has to have zero value as well. So in conductor, electric field is going always to be zero. Well, here are various situations. What happens when the conductor is in the electrostatic equilibrium? If we charge a piece of metal, then, well, that excess charge will exist only on the surface. Inside of the conductor is going to be balanced, electrically balanced. It will still contain charges, but the number of positively charged and negatively charged particles will have the same concentration. Excess accumulates on the surface. Now, the further actually the surface sticks out, the higher is going to be the concentration of those excess charged particles. Now, further sticking out surfaces require that the curvature is smaller, so there is a relationship between curvature of the surface of the conductor and the density of charge. Surface charge density on very curved surfaces is higher than on more flat surfaces. We concluded that electric field is zero everywhere inside of the conductor. Now, if we perform analysis, use Gauss's law and perform analysis similar to that one which we performed for a uniformly charged plane, if you recall now how we considered flux, how we estimated flux, and from that electric field. So if for a plane, we concluded that the magnitude of electric field outside on one side and on the other side of the surface had the same value. However, this time we can see that inside is 0, so we have only outside. However, so which means that flux passes only through the top surface, not through top and bottom like before. So now flux is going to be just magnitude of electric field times the area, and it has to be equal, proportional to the charge inside of the surface. And charge inside of the surface will be surface charge density multiplied by area. Now we have to divide it by permittivity of free space, and we get the expression for magnitude of electric field strength of a conductor, of the field produced by the conductor. So it is going surface charge density divided by permittivity of free space. Now, the surface of any conductor in equilibrium is an equipotential surface. Now, why is it so? Because if we imagine now, because we concluded that electric field has to be upward. And why it has to be upward? Because if I think about a charged particle, let's say that it's an electron, if it were at an angle, then there would be a component parallel to the surface. An electron would travel along the surface. The only way that it cannot travel is that the component parallel to the surface has to be 0, which means that electric field must be up. Well, all right. So now if I use the relationship between electric potential and electric field, let's say that this is point A and this is point B. So I will relate now potential at this point with potential at this point. Potential at point B is going to be potential at point A plus minus line integral from point A to B of electric field vector. Well, if electric field vector is perpendicular to the surface, angle between these two vectors is 90 degrees. So when we calculate the scalar product, referred also as a dot product, we'll have magnitude of this vector times magnitude of this vector times cosine of 90 degrees, which happens to be 0. So this entire integral is going to be 0. And we are getting that potential at point B is equal to potential at point A, which means that the 2 points belong to the same equipotential surface. All right. Now I thought that I do some exercises on the whiteboard to summarize the material which we have discussed so far. So as the first example, why don't we try to calculate electric field and electric potential of the particular location produced by some kind of an object. And as an object, I selected a rod, a uniformly charged rod. So let's say now that in front of this rod at distance x, I have a point and I want to find out electric field at that location. I want to find electric potential at this location. Later on, actually, I will even see, I mean, we'll verify if the relationship between electric field and electric potential, which I've shown you, is correct. All right, so in order to, let's start with electric field. In order to find electric field at this location, I will divide the object into small pieces. It will be always, it's always good to introduce a coordinate system. So let's say that I will choose this axis to be x-axis, this axis to be y, and z is toward us. Now let's say that the length of this rod is L, capital L. Now I have to relate, if I consider a certain segment, I have to relate now electric field at this location due to this fragment. And according to Coulomb's law, it's Coulomb's constant times charge of this piece. Now we have to, I have some, to pick certain variable which will identify the piece. And since I already have x over here, it will be very, I mean, it could be quite dangerous to choose x as the variable of integration, because then you will use one symbol for two quantities and it's easy to make a mistake. So rather than choosing x, I will take the distance from the right-hand side end. I will call it small l. And consistently, the size would be dl. Now, note that since I said that it's a distance from the side, I could also kind of think that l-axis is to the left. L is growing from value 0 for this piece to value capital L at the piece on this side. So if I can use now linear charge density to relate size of this segment with the charge. So instead of writing dq, I will just write linear charge density times the length of this fragment. And now I have to divide it by the distance from the segment to the point of interest, which means that it is L plus X. And there is just one item missing, and because you kind of ignored it, I want you to help me. What is the last factor in that formula? Here I have to put one more factor. A what? R vector. I would prefer that you say it in English. I'll say it's a unit vector heading from the segment toward point of interest. Everybody say it together. All right. Now, consistently with my coordinate system, we have a commonly used unit vector. What is the unit vector heading from the segment toward the point? It's a unit vector to the right. I, correct. So I can write just I. Well, this is differential electric fields produced by that fragment only. So in order to find entire or total electric field, I have to add differential fields, fields due to those differential pieces. So it is integral of dE over entire rod. And here I can already make my mind what to choose as the variable of integration. How about, why don't you help me? So I will be pointing at something, and you will say if you accept it as the variable of integration or not. So how about using Coulomb's constant? No. Okay. Charge density? No. Distance from one end? Yes, correct. I have it already. How about choosing this x? Who votes that x could be the variable of integration? Who votes that it cannot? And those of you who vote that it cannot, you are right, yeah? Because x does not identify pieces. It identifies location of the point. So x in this integral is a constant. All right, now we have to specify the limits. And we have to answer ourselves those three questions, or consider those three factors. We have to make sure that we account for each piece over there. We have to account for each piece only once, and we do not include pieces from outside of the object. Right? So what is the smallest value for L which identifies a piece? 0, correct. I got a hint that it's 0. How about the highest value? L, correct. So here we have integral from 0 to L of that expression. Why don't we pull out constants? So Coulomb's constant is a constant. It's a uniformly charged density, a uniformly charged rod. So charge density is constant in that integral too. By coincidence, this is because I picked such an object. All of them have the same, to each of those pieces, the same unit, the same unit vector corresponds to each piece. They all are to the right, so that I can be factored out as well. How about if I write it at the very end? And so I will be just left with integral of 1 over L plus x. And it's definite integral. You could suggest me a very powerful calculus theorem to find out that integral, so that I don't have to calculate limit of the Riemann sum in order to add those. What theorem would you suggest? The first fundamental theorem of calculus, which allows to find out definite integrals if we know indefinite integrals. Anybody can recognize what is the indefinite integral? Probably it will be in our tables. I think it will be written as a function ax. Oh, how about ax plus b. So if you choose, and in our case, what is the value of a? 1. L, x, I already said. L, right. B, x, correct. All right. So I think that this integral will be 1 over a logarithm of ax plus b. I think so. So this integral over here is going to be logarithm of L plus x in limits from 0 to L, which is going to be equal. Now I have to, consistently with the first fundamental theorem of calculus, I have to plug in values L and 0. So I will have k lambda logarithm of oh no, I'm doing it wrong. I have to square it. Yeah, so if I square it, it will be minus, and I will have 1 over L plus x. Yeah, we forgot about squaring. The formula, Coulomb's law requires that we have to square it. So the result is going to be minus k lambda. When we plug in L, plug in L, we will have 1 over L plus x. And when we plug in 0, we will get 1 over what? X, correct. Yeah, remember that L was the variable of integration. And times I. So we found the expression for the electric field at that location. Well, let's now calculate electric potential at that location. So, differential of electric potential due to a differential fragment is very similar, but it is Coulomb's constant times charge of the segment divided this time by the distance, L plus x. So if we want to calculate potential, I will have to integrate it over the rod, which means again that these are limits from 0 to L. Now this expression. Now see a major difference between this integration and that integration. What's the major difference? Square actually is less important. It is true that here we had square, here we have inverse function. I mean inverse square and inverse. But there is something even more important. Yes, Robert? A what?
Sign.
No.
There's no direction.
One is vector function. Over here we are adding vectors. Over here we are adding numbers. In general, we prefer to add numbers. All right, so let's integrate that. So we'll have k lambda, and now we have logarithm of L plus x in limits from 0 to L. So we will get k lambda logarithm of L plus x minus logarithm of x. So this is potential at point x, and y is 0 over here. This is also electric field at point x 0 on the axis. Now let's see if we calculated it right, and seems to me that there is somewhere an error because, oh no, everything is fine. Yeah, I see that it's fine because I recognize now that how this function is related to that function. Yeah, because now let's try find out this electric field from this function. I mean, in principle, we could not do it because right now we know only potential along the line and how electric field is related to electric potential. So let's say that I want to find x component of electric field. From the function which I found over here, I can find x component. Yeah, generally, how electric field vector is related to electric potential. What do I have to put here? Yes? I think I heard the word. Gradient. We have to take a gradient and, well, opposite of the gradient. But so if I want to find x component, it means that I have to take x component of the gradient of this function. How do we find x component of the gradient? We take the derivative with respect to x. Right, so here I have to take derivative with respect to x of this function. Which means that it is minus derivative of this function. K is constant. I can take it in front of the derivative. Lambda is a constant. I can take it in front of the derivative. So I will keep it here, k lambda. Now what is derivative of logarithm of x? It's what? I can't hear you.
He was just asking what that was, like the D. Like that looked not like a D.
This?
Yeah.
It's D. It's not 2, right? Yeah, but I mean, all right. I mean, I'm glad that you got this. Yeah, it's calculating the derivative over here. Now, jump already further. Let's calculate the derivative of this function. Now, note that now, yeah, because now we have to calculate the derivative with respect to x. So we have to think what happens if we move these points to the left and to the right. We don't calculate the derivative now with respect to L. In order to relate electric field with electric potential, we have to imagine what will happen if we move this point. So we calculate derivative with respect to x. And what's the derivative of it's a composite function, right? External function is logarithm of an expression, and the internal function is a linear function. So when we calculate derivative of composite function, we use the chain rule, correct. So what's the derivative of the external function of logarithm? 1 over the expression. So it is 1 over L plus x. And derivative of linear function of this function, here we have sum of 2 terms. Derivative of L. L is the length of the rod, so it's independent of the location of this point, which means the derivative of L is 0. Derivative of x with respect to x is 1, correct. So I have to multiply it by 1. I will not bother that. Then I have minus, and derivative of this expression will give me 1 over x. All right, and now there is a moment of truth. And what's the conclusion? Should we be happy? Yes, we should be happy. Right, be happy, right, because we found that x component of this electric field, well, agrees with the x component over there. Yeah, this is the same expression. Now here I have vector components, right? I mean, our entire vector. Now, how about calculating y component of electric field from this function? Can I find y component of electric field? Because in order to find y component, what I would have to do, I will have to calculate the derivative, this time with respect to y. Can I do it? What will be? I mean, so I have to, can I take this function? Who votes yes? Who votes no? Those of you who vote no, you are right. Because right now, I'm asking you a question. I mean, this type of a question. I will draw a function, and you probably remember that the interpretation of derivative, geometrical interpretation of derivative. If I have a function, what is the value? Geometrically, what is the derivative of this function at this point? It's the slope of the tangent line, right? So this is geometrical interpretation of the derivative. Now, I'm thinking now about a certain function, and I will give you some information about this function. At this point, the value of this function is this much. What is the derivative of this function? The function which I have in mind. You can't say that. Yeah, because you have to know the function in the vicinity. You have, just from one value of the function, you cannot find the derivative. You have to know how the function varies. And if I come back to this problem, know that we don't have the information in y direction. We only, the formula describes only for one value of y. So we cannot calculate the derivative we would have actually to solve a problem to find out electric potential at that location, x, y. This way we will find appropriate function to calculate the derivative. All right. I prepared also some puzzles now for you. I want to show some demonstrations. This device is called a Van der Graaf generator. And with this belt, if that belt moves, it is going to accumulate charge on the surface, and then it produces electric field. And well, I will put some pieces on top of it, and I'm going to turn on this generator. All right. This is a puzzle, a homework puzzle. Think about it, why they flew off like that. Now, there's one more puzzle which I want also to show you. Here I have a conductive ball. And since I touch it, it is uncharged. And now I'm going to turn on the generator and see what happens with the ball. All right. Think about this too. Now, for the end, I will just want to make something spectacular. I was afraid of doing it earlier because it may affect our audio system here. Well, I think that this effect actually depends on how good is air, and if today I think the air is too wet, so we cannot get a huge spark. Try to explain that too. All right, so this will be all for today. See you Monday.